I am Belayneh, a secondary PhD student from the University of Michigan, where I am advised by Professor Valeria Bertaco. In this demo, I will present you MessageFusion, a domain-specific architecture which utilizes processing in-network solution for energy-efficient and scalable graph analytics. Graphs are everywhere. We encounter them in numerous settings of our day-to-day lives. They are used in representing our social network connections. They are utilized while we are searching for items on the web. We use them in identification of our gene sequences and as a recommendation system while online shopping for items. However, presence of random memory accesses coupled with a very low computational intensity in graph-based applications makes their execution in conventional architectures very inefficient. Specifically, memory bandwidth is wasted since a whole cache line is retrieved for processing only a small vertex data. In order to address this, recent efforts by others utilized processing in memory-based architectures, such as hybrid memory cube, mainly for the higher memory bandwidths they offer. However, fully capitalizing on the available memory bandwidths is still limited by the on-chip network communication. On average, around 60% of the execution time is spent on communication. Hence, in MessageFusion, we try to tackle that by performing or exploiting commutativity in reduction operations through offloading and performing computations inside a network. MessageFusion aims at reducing the overall network traffic. To have a context, let's see the execution flow comparison between a baseline implementation and MessageFusion. Here, we have a 4x4 2D mesh network with the green nodes or sources sending individual messages to the red one or the destination. In the baseline, all messages takes their own path to reach the destination. When it comes to MessageFusion, messages are coalesced while in transit, thereby reducing the overall network traffic. This was achieved by adding small buffer and logic units in the network routers. The buffers increase coalescing opportunity for messages, while the logic units perform computations. Now, our demonstration shows a comparison between MessageFusion and a baseline executing average teenage follower algorithm on LiveJournal dataset. The LiveJournal dataset is a social network dataset with around 5 million users and 69 million connections between its users. The architecture shown on the left is the baseline, while the one on the right shows MessageFusion's architecture. The color gradient shown below each architecture qualifies the magnitude of traffic traversing through each router. A high traffic congestion across a router is represented by red color, while blue color represents lighter traffic. The dial at the top middle shows the total execution time of the baseline and MessageFusion. The lower the cycle count, the better the performance. One can observe that the routers in the baseline network spend most of their execution time being red during the simulation, while the routers in the MessageFusion architecture stay predominantly blue. Hence, MessageFusion achieves lesser traffic congestion as compared to the baseline. We can see from the dial that MessageFusion finished its execution earlier than the baseline, approximately 2 times faster. More information of MessageFusion can be found in our paper. Thank you.